All right. Now that we've spent the first 15 minutes of class trying to figure out where we're going. Not all who wonder are lost. Sometimes that's how it is. Sometimes it takes 15 minutes to figure out where you're going. Just like when we did lab 3, sitting down and doing that little math exercise saved us a whole bunch of money, right? So sometimes we need to go backwards a little bit before we can move forward. I wanted to catch everyone up on kind of where we are because, man, it's coming quick. It came a lot quicker than I expected. It seems like we just took a test, which we did. And then we're going to be taking another one soon. So today, on the 10th, we're going to be out at Oakley at Copeland Cove. I'm going to post quiz 3 sometime tonight. That'll be due by Friday. And then we got spring break. I'm not one of those, bless you, get it. Almost fell out of seat there, you okay? All right. Okay, so we're going to get quiz 3 done, which is going to cover just soil taxonomic classification. All right, it's not going to cover organic matter. It's not going to cover microbes. That's going to be the week after spring break. Okay, and then the week after spring break, we're going to be a little busy right here. We'll get our soil test results back from the quad that we did, and we'll go over how to interpret those soil test reports. We're going to have assignment 2, which is going to cover some of the stuff that you learned in classification, right? So while you're studying for your classification quiz, assignment 2 is going to kind of integrate what we did in lab. And then we're going to have quiz 6, going to be that Friday, soil organic matter and microorganisms, which is what we're going to maybe cover a little bit of today. I might go over some of that, and then next week. And then also calculation 3, is that calculation 3? Which is just going to be our basic rate over analysis math. And so I've had some of our students come and ask me some questions from Dr. Earhart's class that were leading up to what I was going to have on a calculation assignment. So what I'm seeing is that the calculation assignments that I'm having y'all do are relevant in other areas of your curriculum. And I want to make sure that y'all get that. I had a student text me last night at 11:30 saying help, because they didn't understand. But the things that I have taught y'all, once we discussed it a little bit, she went, oh, it's rate over analysis, and this was all I needed to do, and that was all I needed. So y'all do know what you're doing. I just want to keep reinforcing and driving that home so that you feel confident. We're not going to be doing much very difficult math, but just reinforcing some of the things that we've already done. And then we're going to have exam 3 on the 28th. I didn't get to put April in here, but I guess it doesn't matter for y'all because y'all don't come to class on Friday. Because this Friday, right here, was Good Friday. And so then yeah, Madison's on it today, boy. And so, what's that?
We get out for Good Friday.
I think so.
Yeah, we've always gotten out for Good Friday.
Always. That's why it's good.
This is my first time.
Welcome to college.
Here.
And so, and then we're going to go into nutrient management. We'll have a couple of more quizzes, a couple of more labs, and then we're going to be taking the final, and then y'all are out for the summer. Kennedy is excited. It goes quick though, doesn't it? Like, it seems like we just started, but we're almost done. All right? And I think we're going to pick up right here, just to make sure. So I did post the previous, I think it was the end of soil classification. I think soil classification and the beginning of organic matter are all in one video in the YouTube channel. And so, do y'all remember doing this? Do y'all remember taking these notes? This would have been last Wednesday.
Yeah.
And so because I was out Monday, I want to make sure that we're all back on the same plane. We're not missing anything. So we talked about the active fraction. Talked about turning on your clicker. And then the passive fraction. Good, Jacob? Both Jacobs? We talked about the different components of our plant residues. Remember I talked about the cellulose and the hemicellulose. Not that we need to know these bicyclic compounds. A couple of us are turning our stomach a little bit. She gave me the look that you have after you've taken organic chemistry. And so these compounds are difficult to decompose because it takes so much energy to break those phenolic rings, right? And when I say phenolic rings, I mean these. This is a phenolic ring. And so it takes a lot of energy in order to break those bonds so that that lignin can decompose. And remember that the greater the molecular weight, the harder it is to decompose that material. We talked about the rate of decomposition, and so I also got to thinking about this. This is kind of like, you know when you haven't eaten anything all day and you start to get a little shaky? You know, the first thing you want to get is like some candy or something that is going to give you a burst of energy real quick, a soda. Something that's going to provide fast energy. Maybe it's a Kind bar, or maybe it's some Skittles or something. And so those sugars and those starches and simple proteins that are in there, your body can digest those very quickly and get the balance that it needs. And so the same thing goes for the microorganisms. They need energy very quickly. That is the very first thing that they go for. And that is the very first thing they break down so they can get the energy to break down the hemicellulose and the cellulose. We talked about that we talked about aerobic decomposition being greater than anaerobic decomposition, and that it's important for the biogeochemical cycling of our nitrogen, phosphorus, and sulfur. The microbes are using this nitrogen, phosphorus, and sulfur as another energy source in order to decompose those plant materials. We talked about that anaerobic decomposition being much slower because there's no oxygen. So aerobic, oxygenated environment; anaerobic, no oxygen. And the reason why it takes so much more, why it's slower, is because whenever oxygen is there, it's not that it's a complete lack of oxygen, there's just not much there. So it's not readily available. And so whatever is, the microbes are using up almost immediately. And so the processes do not happen as quickly. And that we're going to end up giving off some of these greenhouse gases. And I guess so going this way, this is an oxidation. And then this way would be a reduction, right? So this is going all the way back to basic chemistry, that oxidation it loses, reduction it gains. And in this case, it's going to be oxidation, it's losing hydrogens, becoming more oxygenated. So this is aerobic. And we can see that because of the oxygen that's there. So if the oxygen is not available, the microbes use the oxygen here and then finally give off methane as their respiration, or the byproduct of that anaerobic respiration or decomposition. Right? And so that's just kind of the science behind how that works. So we want to make sure that we have some oxygen so that we're not giving off methane as a greenhouse gas. And if we can keep our carbon dioxide in the soil, then we're not giving off carbon dioxide as a greenhouse gas. The whole goal is to keep the carbon in the soil. Now remember going over these two, autochthonous and zymogenous. Autochthonous organisms, I don't think we went over this in class, did we?
We
did.
We did or didn't?
We did.
We did, okay. It was really weird trying to do that on my computer. I know I talked fast in class and I was even faster on the computer. I was like, slide, slide, slide. Like, yep, they got this, all right, they can stop it. It was real different compared to when I'm in class and I can see what y'all are writing and kind of going.
We actually got all these human substances.
Okay, cool. We talked about the rates of decomposition and those 4 components that are going to influence how fast those decompose, environmental conditions, quality of residues, physical factors, and carbon-nitrogen ratio. Quality of residues being the compounds of the components. We talked about location, that if that leaf falls on the top of the soil, the microbes in the soil don't have the opportunity to decompose that. And then smaller particle size is going to allow for a greater surface area. Those microbes can enter that leaf material and begin to break that down better. Carbon-nitrogen ratio, important to know, 24:1 is about the medium. Less than 20:1, net mineralization. Greater than about 30:1, net immobilization. This will come into play in the next module. But important to know, 24:1. This is where we made it up to the last time, right? This is where we stopped. Okay, cool. Live organisms being the biomass, and that's what we call the microbial biomass. And that's composed of, that's going to be not only our microbes, but also our macrofauna. Next section. Earthworms, beetles, bugs, ants, things, termites, things of that nature. I talked about the debris being identifiable, so like you can kind of tell that that was a corn stalk or a leaf of some sort. But humus, you cannot tell the difference between that. So it has been broken down so much that you can't readily identify that that was a leaf off of an oak tree. I don't think we made it this far in class. So y'all don't have these notes right here. All right, so fulvic acid, lowest weight. And because this molecule is so small, microbes can easily decompose that. They can start to break down to just 1, 2 phenolic rings, a couple of double carbon bonds. Not a lot of energy required in order to decompose that structure. Did I not have anything to write down on that? No. Did we go over this in class?
No.
No, you just watched the video. Look at you. All right. Next we have humic acid. And so this is going to be a little bit heavier, a little bit more intricate molecule, many more of those phenolic rings. And so this is going to be tougher to break down. So it has more resistance to that microbial attack. You might hear of using humic acids to, when I started my PhD, we were looking at humic substances for greater nutrient retention, water retention, but what we found was that because it's so acidic, that it changes your soil pH enough so that maybe the nutrients are held there, but the plant cannot take them up because pH influences nutrient availability. So you can add some humic substances to your soil to possibly change the pH the other way and make it more acidic. And then finally humic with an I. Very intricate structure, very difficult to break down, most resistant to microbial attack. It just takes so much energy in order to break all of these phenolic rings because there's so much charge there. It requires so much energy. This is going all the way back to the equation that had the energy coming off of the end. So some of the ways that we can kind of speed up some of those processes to release those nutrients is by composting. Anybody have grandparents who compost? Parents that compost? And so my grandfather he'd break up all of his leaves and put them in the garden, and then he would go get some horse manure or some cow manure and put it over those leaves so that the microbes had enough energy to break down that leaf material. Composting that. Something that's important, I guess I heard Dr. Duncan doing some vermicomposting with some of his ag education students. And so these are just cool little experiments and kind of things that you can do to increase organic material and organic matter using earthworms. And then you can always sell the earthworms to go fishing with, I guess. All right. So some of the primary benefits of this composting is that we start to decrease that carbon to nitrogen ratio, which is going to minimize immobilization. And so remember we said that about 24-to-1, we have about an even balance between mobilization, immobilization, and mineralization. And that range is like 20 to 30. Somewhere in there you're going to have this very minuscule or minute changes in mineralization and mobilization. Once we get below 20-to-1, we start getting down into 15-to-1. Those nutrients will now be available. And so by doing that, by composting those leaves, those minerals will be readily available rather than putting that out over the garden and waiting for that to decompose. Because then the microbes will use the N that is in the soil to decompose the leaf material that's on top of the soil. Some other benefits are going to be some sterilization. We get some detoxification. So if you remember back from the equation that gives off that 487 kilojoules of energy, now you have that process happening all the time in this big heat. For those of you who have seen compost before in the wintertime, or if you catch it really early in the morning, you'll start to see like some steam coming up off of it. It's because that energy that's being created is causing heat. And so that heat will kill some of those, or sterilize some of those pathogens that might be in some of that plant material. Good time. So we're going to have some differences in soil organic matter based upon our soil orders. And so in our histosols, remember that we had about 20% organic matter in our histosols. These are going to be like our peat bog soils. Our mollisols are going to be probably in the Midwest, on the Great Plains. There's always this thing, I don't know how Ohio is considered the Midwest. Not sure about that. But when I think the Midwest, I'm thinking Nebraska, Oklahoma, South Dakota, maybe getting into Wyoming. The Great Plains region, where they travel the cattle up to Kansas City, they get on the cars, things like that. And so those prairies, they undergo a continuous cycle of where the grass is grazed, where there's some organic material from all the cattle and buffalo and free range animals that are putting that material back into the soil. And then also that natural fires also decompose some of that material that goes into the soil. But our inceptisols and our entosols are new soils. They won't have a lot of organic matter because there hasn't been a lot of crops grown on them. They're just now deep enough to be able to handle some root system. And the more crops you grow, you should be able to increase your organic matter that way, which in turn is going to grow more crops. And since our soils are young and we haven't grown a lot of material on them yet, they're going to be low in organic matter. And this goes all the way back to the pie chart, that 45% of our soils are mineral, about 50% are air and water space, and that 5% is going to be organic matter. And so if you have a soil that's got about 4% organic matter, you're doing super good. But you have an enthosol or an inceptisol that's only got like 1.5% organic matter, you're struggling. So the goal is to increase that organic matter by growing more crops on it. And then the climate is going to influence our organic matter content. Remember that for every 10 degrees Celsius increase in temperature, we get a 2x increase in biochemical reaction. So the hotter it is, the less organic matter you're going to have. So Georgia's sucking, right? Because it's hot. Mississippi, not doing so well because it's hot. Just some of those things to think about. But like as we get up into Nebraska's not so hot all the time, is it? About 50-50. I don't know, I've never lived in Nebraska. Hopefully I don't have to. There ain't nothing there? I hope no one's from Nebraska. Our vegetation is going to serve as a soil source, and then also that our texture and drainage, and so that moisture that's there is going to influence the type of decomposition. So more water, less wood.
In the soil.
Yeah. If we have more water in the soil, less air, and air has oxygen. So anaerobic conditions are going to have less organic matter decomposition. And then the big push in the ag world is ag management and tillage. So we're having to put in more nutrients. We're taking this material off where we used to. Take that material off, it doesn't go back into the soil. So now we're trying to do no-till, where that material stays on the plot and has the opportunity to undergo some decomposition. And then the south, that's good because it's hot and that's going to decompose a lot quicker. And it's going to end up being in the soil. So we're getting away from tillage because what happens when we till?
CO2 in the atmosphere.
How?
Because whenever you bring up the oxygen, it mixes, turns the soil. I'm missing something.
You're on the right track. Keep going.
But anyway, whenever you till it up, you turn the bottom on top, them gases combine with the oxygen, creating CO2 to the back.
Bingo. So by tilling, we introduce oxygen. When we introduce oxygen to our carbon source, what happens to decomposition? It increases, right? And so the result of that decomposition is carbon dioxide. That's the long and the short of that. I mean, you did great explaining that because that's exactly the process. The long and short of it is we introduce oxygen that binds with the carbon and gives off carbon dioxide into the atmosphere. So we're trying to keep our soils stable and hope that they adsorb with a D some of that carbon and it stays in the soil, not in the atmosphere. Great job, Stephen. If you did watch the video, this is kind of where I made it to. And so the important part to this is that when grown in rotation, you get greater soil organic matter added. So corn is going to be a high carbon and nitrogen substance for plant material. Oats are high carbon to nitrogen, but clovers aren't. So clovers break down easier. And if you add that nitrogen source to the soil, the microbes can then break down the previous residues from the corn and the oats. And then in Rothenstedt, they kind of did the same thing. Excuse me. What was important about this study or this experiment station was that the positive effects of adding that manure or adding that organic substance to the soil, the effects were still evident 100 years later. So they added manure and then stopped. the benefits still carried on for another 100 years. So adding carbon to your soil, adding those manures, and I guess this might even kind of run into this new regenerative agriculture push, sustainability, that by adding that manure back to our soils, we're improving the soil health. I just had some information about some of the things that you can do in order to improve some of your organic matter. Cover crops are going to protect your soil. They're going to keep it on site so that it's not off into the ditches. And if it's not in the ditches, it's on the field. Remember, our soils have all of our C. Hopkins Cafe managed by my cousin Mobile Nina. And if they're in the field, our plants are taking them up. They're in the ditch, our plants are not taking them up. This goes back to what I was talking about organic matter. So 1.5% organic matter in a sandy soil is probably good. We're doing really good there. That's home for me. That's Intasols, golf courses, greens, things like that. If you got 1.5% organic, you're doing all right. You start moving up into Missouri, I guess, and even in Tennessee, if you only have a 1.5% organic matter, you're not doing so hot. So it's all relative to texture, climate, things like that. I think I'm going to be able to make it out of this section. We need to be adding our nitrogen back to our soils because nitrogen is going to offset that carbon to nitrogen ratio. It's the energy source that helps the microbes break down the plant material. When they break down the plant material, the carbon goes into the soil. It is the food for our microbes. And so when we have a large microbial population with a large organic matter, that, remember all the way back from the beginning, the 3 sources of pH-dependent charge. Broken edges of clays, aluminum and iron oxides. Functional groups of organic matter, right? So our organic matter is what's going to help our CEC, which is going to hold on to our nutrients, minimize losses to the environment. It's also going to give us that aggregate stability. Because think about it, if I could show you what humic acid looks like, it looks like, y'all ever seen the movie Venom? Like it's like a sticky rubbery type substance. That's what it looks like and feels like. So it's real sticky. Kind of like the goat that's in your gutters. It's nasty. Yeah. So that is what is going to hold your soil together. Yes, my phone barks. We're going to maximize our plant growth, and when we maximize plant growth, that plant decomposes onto the soil. That organic matter goes back into the soil. So it's a give and a take. We're going to increase soil organic matter. It is going to increase crop production. That crop will eventually senesce. It goes back into the soil. So we want to keep our plant material on our soil. Like Mr. Douglas said, that tillage is going to increase oxidation and then also erosion. So conservation tillage is going to slow the erosion, which keeps our soil on site, and then also keeps that carbon in the soil. Just some information about some of the greenhouse gases. If you were to ask someone not in ag, they would not tell you that it's 9%. They'll probably tell you that ag is probably 68% of the world's problems. But yet they need us to feed them. Let you cut us a little slack there. And then some of the ag sources that might be associated with greenhouse gases. I will tell you this though, some interesting information. When COVID hit in 2019 or 20, was it 20? That seems so long ago. That was last year, as a matter of fact, right about this time. Think about it. Last year at this time, y'all went on spring break and didn't come back. It was right at spring break, wasn't it? It was like March 13th, and they said, you know what, we're shutting everything down the whole country. That was a year ago.
Extended the spring break.
That was. So I saw satellite imagery of Beijing, and they showed the satellite imagery of Beijing prior to COVID, like in January, and then after they shut down. The smog over Beijing was so much less, like the carbon dioxide and all those greenhouse gases were much less. Couldn't tell a difference in the ag fields though. Right? Because those were the same. Nothing had changed there. It wasn't like, oh, now all of a sudden we can see all this methane is actually coming from. No, it was actually the cars and electrical fossil fuel combustion. So y'all probably have to fight that a lot as you continue on in your careers, knowing that we are not actually as big a problem as the media is making us out to be.
Just easy.
But our carbon dioxide levels are increasing. I think that's it. That's all I got. I will make sure that I get you the information that you need in order to get to where we're going for lab, okay? We'll see y'all there. Thank you so much.